Air travel has taken off, with a rate of climb which puts it amongst the world's fastest growing industries, carrying more people at higher speeds and altitudes than would have been imaginable even 40 years ago. To make this possible, we accept being sealed into metal tubes, cut off from the natural environment and dependent on man-made devices for the air we breathe. But air quality today is a major issue. At ground level, at any rate, standards define maximum amounts of pollutants in the indoor environment. Take carbon dioxide, CO2. This can rise from 300 or 400 parts per million in the open air to a couple of thousand parts per million or more in a room full of people, solely because our own lungs are giving it off all the time. And where CO2 builds up, it indicates a stuffy atmosphere. So just how effective are the devices which supply the air in our airborne metal tube? A few people, especially contact lens wearers, can sometimes feel uncomfortable on long flights, just as some can in offices, trains, buses, and so on. Some complain of dry eyes. Some smell traces of cigarette smoke, even in non-smoking sections, and may think that that's the cause of their discomfort. But what are the facts? The Center for Indoor Air Research, a US-based non-profit organization, has now sponsored the most extensive study of aircraft cabin air quality ever undertaken. Its fieldwork and laboratory analyses were conducted by TNO in the Netherlands, one of Europe's leading independent research laboratories. And the study was made possible by SAS, the Scandinavian airline system.
First of all, we have a general interest of environmental questions. We have a working group working at airports with, for example, pollution questions. And secondly, we care very much about passengers and crew on board, and there are not many studies made on air quality, so we wanted to participate for that reason as well. The third reason is that we are in the process of buying new aircraft, and we wanted this study to be an input for the aircraft manufacturers for future improvements in these systems.
Cabin air quality studies had been run before now, but very few took a comprehensive look at the factors which might affect air quality, including tobacco smoke. Reviewing the findings that did exist, Dr. Larry Holcomb, a specialist in the field, has stated, "We have known for some time that a variety of factors in the aircraft cabin could affect cabin air quality. The SAS study was designed to investigate in a systematic and comprehensive way some of the more important factors in the cabin air quality equation." The new program started out with an advantage over its predecessors. PASS, the portable air sampling system, was developed by TNO for this study to provide a much more complete profile of cabin air quality. 48 SAS European flights carried 4 PASS units, one each in Euro class, that is, business class, and tourist, smoking and non-smoking, on seats chosen by random selection and changed about from one flight to another. On average, flights were 75% full. The units continuously recorded data on temperature, barometric pressure, relative humidity, and respirable suspended particles, and collected nicotine, carbon monoxide, and carbon dioxide throughout each flight. A TNO technician travelled with each unit, while a coordinator monitored the relevant flight details. Straight from the aircraft, each unit went to a nearby base station. There, its electronic data were fed into a small computer, and its air samples analysed for their carbon monoxide and carbon dioxide content. Then all the resulting data, with the tubes and filters used to collect nicotine and respirable suspended particles, that is, material light enough to float in the air and small enough to be breathed in, went to TNO's laboratories at Delft. Here, the precise amounts of nicotine collected were measured and recorded by gas chromatography. Then, to determine the amounts of respirable suspended particles, RSPs, the PAS filters were weighed on microbalances. All the data were then fed into TNO's mainframe computer, which was to produce the final results. Various versions of DC-9 and MD-80 aircraft were used, and the results showed only small variations amongst them. These were converted into averaged values of cabin air components collected continuously during flight, shown by class and section. For RSPs, these values were 60 micrograms per cubic meter in business non-smoking, 250 micrograms in business smoking, 160 in tourist non-smoking, and 220 in tourist smoking. For nicotine, the values were 5, 41, 21 and 32 micrograms per cubic meter. Putting these values into proportion, 1 microgram is 1/100th of the weight of a single grain of sand. For carbon monoxide, the values in parts per million were 0.6, 1.1, 0.8 and 1.1. And for carbon dioxide, the parts per million were 1310, 1310, 1270 and 1430. And 1 part per million, 1/10,000th of 1%, is equivalent to 5 grams of grain out of a truckload of 5 tons. So the results show that the air quality in our sealed metal tubes is less than perfect. Not surprising, since the same goes for our homes and workplaces. But just how imperfect is it? We know it can occasionally cause discomfort, but can it be harmful to health? There being no comprehensive standards for aircraft cabins, the team answered this by comparing their results with those set by various authorities for an entire working day on the ground. Here again are the carbon monoxide values in parts per million: 0.6, 1.1, 0.8 and 1.1. And this at 50 parts per million is the workplace standard set by the US Occupational Safety and Health Administration. So the highest average cabin rating was 97.8% better than that figure. It was also nearly 87.8% better than the much stricter 9 parts per million sent for the general population by the US Environmental Protection Agency and the World Health Organization. Then the nicotine in micrograms per cubic meter: 5, 41, 21 and 32. And this, at 500 micrograms, is the workplace standard set by OSHA. So even the highest aircraft cabin level was 91.8% better than the OSHA safety standard. Then thirdly, the carbon dioxide averages in parts per million: 1310, 1310, 1270 and 1430. And even the highest of those is 71.4% better than the 5,000 parts per million OSHA standard. It is also 42.8% better than the much stricter building standard of 2500 from the American Society of Heating, Refrigeration and Air Conditioning Engineers, though far-reaching new ideas on air quality have now prompted a new proposed ASHRAE standard of 1,000 parts per million. So, from these comparisons with standards, there are no relevant standards for RSPs, only CO2 could be thought to raise a question. But that's no surprise. We've seen that high CO2 levels in a crowded space always suggest stuffy air, whether people are smoking or not. And here components can build up to produce irritation of the eyes, for example, and of the upper respiratory tract. And other factors emerged too. For the study showed average humidity of only 25% throughout the aircraft, against the 30 to 70%, which is the generally recommended comfort level, and temperatures from 23.4 degrees Celsius to 24.2 degrees, 75.6 degrees Fahrenheit. While high CO2 levels indicate reduced fresh air, high temperature and low humidity may cause actual discomfort. And what all three have in common is that their levels, like those of tobacco smoke, depend on ventilation. Ventilation design varies little amongst modern aircraft. Air is tapped from the engine intakes and goes through an air conditioning pack into a mixing chamber. Then it's ducted along both sides of the cabin, a separate supply goes to the flight deck, entering the cabin through a continuous grill below the overhead lockers. Then the airflow is downwards, out through floor-level grills and back beneath the floor to an outflow valve near the tail, although in the MD-80, 30% of it is recirculated through a filter. The design works well in reducing drafts, once a common cause of complaint. But the sighting of the outflow grills at floor level is a particularly weak point, for this is one of the two places the authorities specify for hand baggage. This can block the grills and hamper the row-by-row elimination of used air, which was the very purpose of the design. And that's one reason why airlines insist on only a single hand baggage item per passenger. Meanwhile, the placing of the outflow valve near the tail may encourage the backward drift of air constituents, which the scientists noted. So it does look as if the airlines could be better served by the aircraft manufacturers. Designers should take a new look at ventilation, providing more fresh air, better distribution of it, and better elimination of used air. Meanwhile, if existing systems sometimes cause discomfort, is that a health issue? The team found no evidence to support such a notion. They concluded that, although cabin air quality is affected by the ventilation, it is acceptable. That any acute, that is immediate and short-term, effects of cabin air are confined mainly to local irritation of eyes, mucous membranes, etc. That these effects are likely to be weak, rapidly reversible, they very soon go away when you leave the aircraft, and not threatening to anyone. That even in the case of compromising medical conditions, those, that is, which could be affected by air travel, significant worsening is unlikely. And given the concentrations found and the fraction of our lifetimes we spend in the air, cabin air contributes insignificantly to the total effects of indoor air pollution, even for flight attendants or the most frequent travelers. Earlier, we quoted from Dr. Holcomb's review of previous studies of cabin air quality. How does he view these latest results?
The recently completed SAS study served to confirm what earlier studies have shown, and that is that airline air cabin quality is generally quite good, that there is no risk to health from breathing that air. That doesn't mean that people couldn't be uncomfortable at times. If humidity is very low, and if the temperature is too high at times, they may feel uncomfortable. There may be ozone, although ozone was not measured in these particular studies. Ozone at flight altitude, if not corrected for in the cabin, could cause some irritation of the respiratory tract. Carbon dioxide levels, if they're high, the people may feel stuffy. Overall, I would say that this study shows us that there's not a health risk involved, that designers of aircraft certainly might take into account that there is some discomfort at times and provide better ventilation techniques on these aircraft. But overall, it shows us that there's pretty good air quality there.
So while we sit sealed into our airborne metal tubes, it does seem that we can relax in the knowledge that the air we breathe is certainly doing us no harm, that any discomfort a few of us might feel will be only temporary, and that conditions compare remarkably well with those we can experience any day on the ground. There is room for improvement in the air we breathe in flight, just as there is in most other aspects of modern living. We hope that aircraft designers will use the valuable information from studies like this to achieve that improvement in the future.